It didn't arrive with drama or thunder, just a whisper of light across a Chilean sky. On July 1st, 2025, a small telescope of the Atlas survey picked up an unfamiliar trace gliding silently through the darkness. Its motion didn't fit any known comet. Its path was too steep, too fast, too foreign. And that's when astronomers realized this was not one of ours. It was 3I Atlas, the third confirmed interstellar object ever to visit our solar system. What followed wasn't just another entry in an astronomical catalog. It was a moment that cracked open the boundaries of what we thought we knew about interstellar travel, not for spacecraft, but for nature itself. As its trajectory was reconstructed, one truth became impossible to ignore. 3. Atlas wasn't just passing through the solar system, it was cutting across it in a way that no known object should. Its hyperbolic orbit was so extreme that even the faintest gravitational whisper from the sun could not hold it. It was moving at roughly 37 miles per second, a cosmic escape velocity from everywhere, heading nowhere. But what truly unsettled scientists wasn't its speed. It was where it began to change. At over 500 million miles from the sun, where even most comets remain frozen and dormant, Atlas began to breathe. Gases escaped from its surface, forming a faint coma rich in carbon dioxide. The activity shouldn't have started that far out, not in temperatures colder than minus 300 degree Celsius. Something about this object was defying the physics of sublimation itself. We had seen visitors before, Oumuamua's cryptic shape, Borisov's icy breath, but this one was different. Not just another traveler, not just another anomaly. Its path was rewriting our equations of the deep interstellar medium, and perhaps our place inside it. In the first days after its detection, astronomers across the globe turned their instruments toward the new visitor. From Hawaii to Chile, from Mauna Kea's infrared eyes to the very large telescope's polarimetric sensors, the world focused on a single point of light, moving with deliberate indifference across the star fields of Sagittarius. Its motion was unmistakable, a hyperbolic trajectory with an eccentricity greater than 1.08, confirming that it had come from beyond our sun's gravitational grasp. But it wasn't the orbit alone that caught attention. It was the subtle flicker in its brightness, rhythmic, unpredictable, and deeply puzzling. As the object approached 5 astronomical units from the sun, about the distance of Jupiter's orbit, it began to shine more strongly than expected. Data revealed an active coma dominated by carbon dioxide, with only trace amounts of water vapor. That ratio was unlike anything observed in solar system comets. The spectroscopic signature hinted at a body forged in an environment deprived of water ice, but rich in volatile carbon compounds, perhaps a region beyond the frost line of another star, or within a cold molecular cloud that had never known sunlight. Yet, the true puzzle emerged when researchers analyzed its polarization, the way its scattered light twisted through space. Unlike any comet ever recorded, 3I Atlas displayed a strongly negative polarization even at small phase angles. In simpler terms, it was scattering light backward, in defiance of what cometary dust typically does. That strange behavior suggested a surface covered by grains smoother, darker, and possibly more compact than expected, as if the object had endured long interstellar erosion, sandblasted for eons by cosmic dust and radiation. Some scientists proposed that its surface had been chemically altered by cosmic rays during its journey between stars, creating a crust of organic carbon compounds that trapped gases deep below. Others suggested a more dynamic explanation, that as the object left its parent system, violent tidal interactions might have fractured its crust, leaving it primed to release gases at unusually large distances. But then came the shock that deepened the mystery further. High-resolution images revealed a faint secondary structure near its tail, an antitail, a stream of dust appearing to point toward the sun rather than away from it. That inversion of geometry could only happen under specific and rare conditions, when sunlight pressure and particle velocity combine in a narrow balance. It implied an extremely delicate, possibly unstable structure, one that might not survive its closest approach to the sun. If 3I Atlas was a messenger from another world, its body was already whispering a message in the language of physics, one that few had yet begun to translate. And then, as it drew nearer, the object did something that no model had dared to predict. By late August 2025, telescopes tracking 3I Atlas noticed a deviation. Small, almost imperceptible at first, but undeniable. Its trajectory was shifting slightly from predictions. For days, teams at the European Southern Observatory reran their models, accounting for every known gravitational influence: Jupiter's pull, solar radiation pressure, even the Yarkovsky effect from heat re-emission. Nothing fit perfectly. The deviation was real, and it was coming from within the object itself. Non-gravitational acceleration. That was the technical term. It meant the object was changing speed or direction without any external force. The most logical explanation? Outgassing. Jets of vaporized material were escaping from its surface, pushing it gently but persistently off its expected path. But here again, 3I Atlas refused to behave like any known comet. Typical comets show symmetric, sunward acceleration as ices vaporize. Atlas's push was inconsistent, sometimes sunward, sometimes lateral, as if jets were erupting unevenly from hidden fractures. Spectroscopic observations from Gemini South suggested that CO2 outgassing dominated over water vapor by more than a factor of 10. The pattern implied volatile sources buried deep beneath a dark, carbon-rich crust. At 4 AU, the coma brightened again, expanding to over 60,000 miles in diameter, enormous for an object barely a mile across. The material reflected sunlight with an unusually flat spectral slope, giving it a matte, ash-like glow. The comet seemed to be losing mass faster than models predicted, shedding layers of dust and gas as if it were unraveling. Astronomers began to suspect that 3I Atlas might not survive perihelion. Its structure appeared fragile, perhaps fractured by the stresses of rapid heating. Polarimetry hinted at particles disintegrating into finer dust, a telltale sign of fragmentation. The object, once solid and ancient, might be dissolving in real time before human eyes. Still, there was a quiet awe in the scientific community. This wasn't just data, it was the autopsy of a traveler that had crossed the galaxy to reach us. Each measurement, each spectral line, was a memory, a record of a different star's formation, a relic of a system that had died long before Earth even cooled. Some speculated that the excess CO2 meant 3I Atlas formed in a protoplanetary disk colder and richer in carbon than our own, possibly near a red dwarf star. Others suggested an origin within the outer regions of a binary system, where gravitational instability could have ejected icy debris into interstellar space. But none of that explained why it began venting so early, or why the object's internal chemistry seemed to react to sunlight differently than any comet known. As September unfolded and Atlas approached the inner solar system, the mystery deepened. Its light curve fluctuated violently, as if something inside it were fighting to hold together. And then, just weeks before perihelion, a new signal emerged from the data, one that changed the tone of the entire investigation. It began with a subtle irregularity in the light curve, a small dip that repeated every few hours. At first, it looked like noise, the kind of statistical artifact that appears when dust clouds distort the light from an active nucleus. But as data accumulated from multiple observatories, Gemini, Subaru, and the JWST, the pattern grew clearer. The brightness of 3I Atlas was oscillating with surprising regularity, not chaotic, rhythmic. When the frequency was analyzed, astronomers concluded that the object was rotating, but not smoothly. The light variations suggested a complex, tumbling motion, with multiple rotational axes shifting unpredictably. In other words, 3I Atlas was spinning itself apart. That single insight reframed everything we thought we knew about its behavior. The erratic jets, the inconsistent acceleration, the asymmetric coma, all of it could be the result of a body that was no longer intact. The surface fractures were venting CO2 from multiple directions, changing as the object rolled, flipped, and precessed in space. The faint anti-tail seen weeks earlier now made sense. It was debris, dust grains following divergent paths from a disintegrating nucleus. By mid-October, new polarimetric readings indicated a steep drop in albedo. The surface was darkening rapidly, perhaps due to fresh material being exposed from within. The coma, once faint and smooth, began to show streamers, delicate filaments curling away from the nucleus, evidence of fragmentation. It wasn't just outgassing now, it was structural collapse. Astronomers at the Lowell Observatory compared the event to comet C2019Y4, Atlas, which broke apart dramatically before perihelion in 2020. But there was one major difference. 3I Atlas was not a child of our sun. It was born under another sky. Its ice chemistry, its dust cohesion, its thermal tolerance, all were foreign. Its disintegration was telling us about how other solar systems fail, how their comets live and die when thrust into alien light. And still, there lingered something uncomfortably poetic in the data. The more we measured it, the more it seemed that this interstellar traveler was erasing itself, leaving behind only traces of what it once was. A cosmic biography dissolving in sunlight. Yet even as its body weakened, it carried within its vapor a fingerprint of its birthplace. JWST's near-infrared spectra picked up faint signatures of cyanide and complex carbon chains, molecules that could only form in extremely cold, dense nebulae. That meant 3I Atlas had likely originated in a region of interstellar space more ancient than our own solar system, possibly near the edge of a molecular cloud that had collapsed to form a distant star millions of years ago. We were watching not just an object die, but a piece of cosmic history unravel, a fragment of another world returning to dust under our sun's gaze. And then, just days before it reached perihelion, the object's brightness spiked violently, as if something inside it had finally given way. October 25th, 2025. Only 5 days before perihelion, the object that had once drifted faintly against the stars now flared with blinding intensity. Observatories across both hemispheres registered the surge simultaneously, a magnitude jump so abrupt that it could only mean one thing: 3I Atlas was breaking apart. Within hours, the JWST and the VLT captured images that confirmed the suspicion. The nucleus had fragmented into at least 3 discernible pieces, each trailing its own faint tail of gas and dust. It was a moment both breathtaking and tragic, the first direct observation of an interstellar body disintegrating under the heat of our star. For scientists, it was also a goldmine. Spectral analysis showed something extraordinary. The newly exposed interiors of the fragments emitted stronger signatures of carbon monoxide and hydrogen cyanide, compounds that had been hidden beneath the crust. Their ratio, unusual even by interstellar standards, suggested that this object had never been warmed above -350 in its entire existence before entering our system. It had remained frozen for eons, its molecular memory intact. Now, in a single solar week, that memory was evaporating into space. The fragments behaved chaotically. The largest retained a faint coma, but the others seemed to dissolve rapidly, creating an expanding cloud of ultrafine dust. Radiation pressure from the sun pushed that dust into a wide fan, forming a shimmering veil stretching more than 200,000 miles, a temporary glowing scar across the void. For dynamicists, this event was a key. By analyzing the motion of the fragments, they could infer the object's density, tensile strength, and internal cohesion, data no probe could ever have gathered directly. 3I Atlas, it turned out, was astonishingly porous. Its density was perhaps no greater than 0.1 grams per cubic centimeter, lighter than aerogel, barely holding itself together. That explained everything: the erratic rotation, the asymmetric outgassing, the premature activity at 5 astronomical units. It wasn't a solid relic. It was a fragile lattice of ice and dust, sculpted by light years of radiation. As its disintegration unfolded, one question began to dominate scientific discussions: how many more like it were out there? If Atlas was this delicate, how many interstellar fragments had already passed through our solar system unseen, too faint, too short-lived to detect? The discovery transformed astronomy's priorities overnight. New surveys were planned, telescopes recalibrated, and algorithms rewritten to detect transient hyperbolic visitors before they vanished. The cosmos, it seemed, was far more connected than we ever realized. These objects weren't intruders. They were the dust between civilizations of stars. But as we gathered every photon we could from the fading debris, a final twist emerged. One that would reframe our understanding not just of interstellar visitors, but of the invisible highways threading the galaxy itself. In the weeks following the breakup, scientists turned to the data that mattered most: trajectory reconstruction. Each fragment of 3I Atlas had deviated slightly from its predicted path, spreading into a fan-shaped pattern across the sky. At first glance, this was normal. Lighter fragments accelerate faster under solar pressure. But when analysts plotted the motion precisely, something unexpected emerged. The smaller debris didn't simply drift outward in random directions. Their velocity vectors aligned along a subtle curve, a trajectory that traced back not to a single point, but to a narrow corridor in interstellar space. A corridor shared, astonishingly, by Oumuamua and Borisov. The odds of such alignment were astronomically small. 3 separate interstellar visitors from different epochs, passing through the same approximate inbound region, within a few degrees of galactic longitude 275. That region pointed toward the Carina-Sagittarius arm, a dense intersection of molecular clouds and star-forming regions nearly 10,000 light-years away. It was as if our solar system had been brushed by a faint stream of material, a cosmic river of debris, flowing silently between stars. The idea, once speculative, began to gain weight. Perhaps the interstellar medium wasn't as chaotic as we believed. Perhaps it had currents, gravitational filaments sculpted by the orbits of massive stars and remnants of ancient supernovae. If 3I Atlas had traveled along one of those currents, it might have been part of a larger population. Millions of icy fragments wandering the galaxy, following invisible highways of motion carved by stellar gravity. Our sun had simply drifted through one of these lanes, catching stray travelers in its pull for a fleeting moment. That realization carried profound implications. It meant that interstellar objects weren't rare cosmic accidents. They were emissaries of a vast, ongoing exchange between worlds. Each one carried not only the chemistry of its home system, but also the story of the galaxy's hidden dynamics. In late October, just 2 days after perihelion, the fragments of 3I Atlas had dimmed beyond detection. Yet, the data they left behind now hinted at a map, a galactic topography written in trajectories. By comparing their motion with the solar system's path through the local interstellar cloud, astronomers could begin to chart the unseen structures connecting stellar neighborhoods. We had thought of space as empty, an ocean of isolation. But Atlas was showing us that even emptiness had texture, that even silence could have structure. And then, as simulations projected forward into the next decade, something startling appeared. A faint, predicted crossing of another hyperbolic body, due by 2031, following almost the same galactic vector. Was 3I Atlas merely one fragment of a greater chain? When that simulation result surfaced, the prediction of another incoming object from nearly the same galactic direction, the conversation among astronomers shifted from wonder to urgency. If 3I Atlas was part of a stream, then it wasn't a lone messenger. It was a fragment in a sequence, a breadcrumb trail left by something larger, older, and more complex than any single comet could represent. Researchers began to revisit data from past sky surveys, searching for faint, short-lived anomalies that might have been missed. A few candidates emerged. Weak detections on archival plates from the early 2000s, even the 1980s, all moving too fast to be bound by the sun. No confirmation could yet be made, but the pattern hinted at repetition. Something, somewhere, was sending debris our way at predictable intervals. Theorists proposed a stunning possibility. An ancient stellar system disrupted by a supernova millions of years ago could have ejected a cloud of planetesimals into interstellar space. Over eons, that material would stretch and thin into a vast stream of icy fragments. Our solar system, drifting through the galaxy, might have just entered that stream's edge. If true, this meant that the interstellar visitors we'd seen, Oumuamua in 2017, Borisov in 2019, Atlas in 2025, were not isolated accidents but parts of a much larger galactic mechanism. A circulation of matter between stars, each fragment a sample of a world destroyed, each orbit a message about how galaxies recycle themselves. For planetary scientists, this revelation redefined the scope of interstellar chemistry. By analyzing the volatile ratios in these travelers, CO2, CO, CN, and organic compounds, we could map the diversity of other planetary nurseries without ever leaving our system. The objects weren't just curiosities, they were probes of natural origin, bringing samples from light years away straight into our observational reach. And beyond the technical wonder, there was a human moment, a quiet realization that our solar system was not an island. The same processes that shaped our planets were happening everywhere, endlessly. Every fragment like Atlas was a physical reminder that the universe is in constant exchange, not through communication or intent, but through the silent physics of motion and loss. The data from Atlas's disintegration now lives archived across global observatories. Its vapor, once a frozen relic of another sun, is now dispersed among the atoms of our own neighborhood. It has become part of us, part of our cosmic story. But before scientists could even begin to close the chapter, the final data point arrived from JWST. Faint, almost an afterthought. A residual CO2 emission, still detectable days after the object's apparent disappearance. It shouldn't have been there. Something was persisting in the void. Even after the nucleus had vanished into sunlight, 3I Atlas refused to fade completely. The faint carbon dioxide trace detected by JWST lingered, drifting through the vacuum like a ghost of chemistry that refused to die. It was a signature without a body, the spectral memory of an object that had crossed light years only to dissolve at the doorstep of our sun. That lingering emission became the final paradox. If the fragments were gone, what was still releasing gas? One theory suggested that microscopic grains coated in volatile carbon ices continued to evaporate long after the main nucleus disintegrated, a slow fading of the object's essence. Another proposed that solar radiation had charged the remaining dust, creating an extended plasma sheath where trapped molecules were still recombining. Either way, 3I Atlas was teaching us that even death in space is not absolute. Months later, when the orbit calculations were complete and the data published, something deeper settled in the minds of those who had watched it. The object had not merely passed through the solar system, it had rewritten how we define connection between stars. It showed that interstellar space is not an abyss, but a vast, breathing network of motion, a bridge of dust, gas, and memory linking worlds that will never meet. In its quiet disintegration, 3I Atlas became something larger than itself, a reminder that every atom is a traveler, every orbit a continuation of another story. Do you believe this discovery changes everything? Or is it just another cosmic coincidence? Tell me below.